All right, everyone, we are talking about Chapter 11, more on functions. And you've learned basic functions. Now we're going to teach you some different ways to write them and some different ways to use them. Let's do first a refresher on the basics, just with the terminology and the anatomy and all that. Then I'm going to talk about this concept of calling a function versus referencing a function by name. And then we'll look at how to create functions that don't have names and different ways to use them. And then I'll talk about higher order functions. What happens when you have a function that can take a function as an argument so that you can operate on something with a very specific function. And I'll give you some different examples of that. And then I'll talk about recursion, which if you've done your reading, you're probably, your mind is being blown a little bit by recursion, and that's normal. So hopefully, a little discussion and a little bit of additional examples will help you out with that. Okay, so just as a refresher, when you define a function, you use the function keyword. You create parameters as variables to represent the input for that function. And then if you are returning output, you use the return keyword, right? And then when you go to, let's just look at this first. Right, so there's the keywords, function and return, the parameters, and then of course the function name and the value that's being returned. Now, if you're going to be executing a function, you have to call it with the parentheses. And that actually makes sure that all the code inside the function body in the definition will get run. And then of course, if there are any parameters, you want to pass in arguments for those in the same order. So here we have, this value. We're going to calculate the apples remaining by using our subtract nums function and passing in the total apples and the apples eaten. And so those are the arguments that we're passing in. Now they're variable names because we're, using something that exists that represent values, but they're still arguments. And they are the real things that we're passing in for these parameters N1 and N2. So then, of course, apples remaining is
3.
Yep, 3. So that's functions, right? Let's talk about calling versus referencing. So I just talked about calling a function. You use that, the parentheses after the name, and that executes the code. What if you only want to reference it by name? There's some reasons why you might need to do that. So you can reference it by just leaving off the parentheses. And that will allow you to do some things like creating an alias. So this idea of an alias basically says, we have a function, it exists in memory at a specific location in memory, on your hard drive or whatever. And we are just going to create an alias that points to that function. So here's an example. I've got an array of numbers. I'm creating a function that can make a copy of that array. And all I have to do is, give it that array and it'll make a copy of it. So all I do is just take a slice from 0 to the end, and that's a copy. It's a subarray, but it's all of the elements, right? That gives me a copy. So I can actually create an alias first for this function and just give it a different name. So how would I do that? What would I put after the assignment operator there?
Get copy of array.
Yeah, without the parentheses, because I'm not trying to call it and get a return value. I'm just saying I want to create an alias. Okay, so now if I call get copy of array and I pass in nums, then I should just see the same array, right? Because I just took a copy of it. What happens if I say get copy and pass in nums?
Same thing.
Yeah, same thing, because it just points to the original function, right? Any idea what I would get if I just tried to console log get copy? It's a little wacky, so it's okay if you don't know.
Description of the function.
Yeah, it's going to say something like this. It's going to say, hey, that's a function, and here's the original function name, get copy of array. So it actually tells you you're just referencing a different array, and you're just referencing it using an alias. If I check type of get copy, any idea what I would get with type of?
Function.
Yeah, it's a type. So, you can play around with this and get a sense of kind of how this is working behind the scenes. But essentially, we declared this as a variable, let get copy. But if we ever were not sure what get copy was, we could check it out with type of. We could try to log it, and it would say, oh, yeah, that's a function. And here's what it points to. And it all, was stemming from originally a function we already had defined. Okay. So that is the idea of referencing a function and creating an alias. I'm going to do an example of this, but before I do, I need to introduce today's theme, and I'm going to have to resize my window a little bit because it's very performance intensive, and it won't show up right if I do it too big. All right.
Ah.
You remember this? All right, so there you go. Clearly, we have a theme. And yeah, I did not create this. It was created by this guy, Wilbjorn. And you can, if you play this, and you'll have the link to this later, you can click on this to go see his stuff and, different things he's got, his on his GitHub and whatever. Really cool stuff. He's got a lot of neat things. And I learned a lot. I mean, if you look at the code, it is not basic, it's very advanced, and I have learned a lot just in the process of customizing this. I had to figure out quite a lot of what he was doing, which is pretty cool. Okay, so we have a theme. Let's do it. So this idea of calling versus referencing, let's go ahead and start. We have an existing function, say hello, and it returns hello name. Now I can use it, and I can say, let's log the return value from that. So I'll call it and pass in Steve. Okay. And I'll, nope. Node, more on functions. There we go. Hello, Steve. Okay. Now let's print the reference to the function. So I will just put the name, but I won't call it. And when we do that, it says function is say hello, and it gives us the information about it. Okay. If I wanted to check the data type, I can do that. And we see function as expected. Okay, so now we want to create an alias. Let's just say, let hi there equal say hello. Now, I'm doing this, I actually would prefer to use const, but I'm going to talk about that in a minute, about why you might choose to use const instead when you're dealing with functions. I'll keep it this way for now. So let's use it as an alias and actually use it as the function and pass in Nancy. And then we will also print the reference. And I'll just print the name of it. Hi there. All right. Okay, so we see hello, Nancy, and then it says function is say hello. So it's still pointing to the original function, even though we called it and we referred to it here using the alias name. Okay, so that's a helpful thing for you to know, because sometimes you'll run into situations where you've got a name for something that's actually representing something else. And in fact, we're going to do a little bit of that ourselves in a minute when we start working with anonymous functions. So let's talk about that. Anonymous functions. What happens when you have a function that doesn't have a name? You can actually do that using the syntax you already know with the function keyword and just leaving the name out. And yeah, otherwise the syntax is the same. Okay. So one way to do this would be to store it in a constant, and then you do have a name that you can use. And the reason you would use a constant is to prevent that function from being overwritten by another value. Because as we know in JavaScript, you don't provide types when you declare your variables. So JavaScript doesn't really know what type something is until it can infer it from the type of data you assign to it. And it's very possible that you could go later and say, I want to use this same variable name and assign something to it. And now suddenly your function is gone because you've reassigned a Boolean or, a string to it or something. So constants will prevent that from happening. And one thing that students ask about, so I will just mention this now, is, well, yeah, but if you do that, then how can you use the function with multiple values? So here's the distinction. When you're working with a primitive like a string or a Boolean or something, or a number, a constant means you can't overwrite that single value at all, right? But with objects and things like functions, all you're doing is providing the structure or the definition or something like that. And it doesn't mean you can't still use the function as it's intended and pass in different values and get different results. It just means this definition cannot be overwritten. So it's good practice, and pretty much every senior dev I've ever worked with, does it this way. So you want to store functions in a const, preferably. So we'll do that, and then we have a name, and that essentially is our alias now for this function that does not itself have a name here like we normally would see. And you'll notice that there is a semicolon here. That's because this is one line of code. And what's happening here is this entire function definition is just being provided as the value to be stored in that constant. So you haven't seen a function definition done this way before, but this is how it's done. So that's a single line of code. And now if I call capitalized Tennessee, I expect to see, oh, actually, I have more bullet points. Let's get to that in a second. Yeah. Yeah, this is another important point. Functions, you may recall from last time, can be defined anywhere, and you can call them from above, you can call them from below. But the minute that you actually just store a function definition in a constant, it follows the rules of constants, which is that JavaScript reads it from the top down. It's not going to make note of that as a function until it actually starts executing from top down. So you have to declare it above the code where you plan to call it. That is an important distinction. Let's see. Yeah, and then later you'll just use that constant name as the alias, and there's my bullet point about the semicolon. Okay. So yeah, so we go to with these keywords, constant and function both being used here. And then we give it the name as the name of the constant, and that's the alias. But of course, it still has a parameter, it still returns, it's got the semicolon here. Okay. And if we capitalize Tennessee, we get Tennessee with the first letter capitalized, right? If we have the return value from that. Okay. So this is the syntax for storing a function definition in a constant as an alias. Let's go ahead and just do an example of this, and then I'm going to talk a little bit more about when you might use anonymous functions, because there are different ways you could do it. So we're going to come down. I'm going to write an anonymous function and store it as a constant that will allow us to decode messages from Will in the upside down using the Christmas lights. Everybody remember that? Okay, so the letters A through Z will be numbered 1 through 26, and the space will just be the 0 since everything's 0 indexed, right? And so we're going to write a way to decode this, and then we'll be able to process these messages and find out what the messages are. Okay. So I'm going to start with const read message in lights. And now I'm going to store a function definition in that. So I'll create an anonymous function, function, and then just give the parameter array of nums. So we can pass in any array that we want to. And then after here, I'm going to put that semicolon. But now let's do the body of the function. The first thing I need to do is have something to refer to for all the letters, right? So I'm just going to create a string called alphabet. And I'm going to put that space at the beginning for index 0. And then we're going to go 1 through 26 will be all the letters. So A, K, L, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. There we go. All right. And now I have to create a message. This is going to be an accumulator pattern, right? We're going to go through an array like this and process them one at a time and build a string. So it's a string building. So I'm going to create the message that I want to create is going to be an empty string to start with. And then I can just loop through with a classic for loop for iterating through the entire array. 1 less than the length, we will increment by 1 each time. And then I can just build this string and say, let's add on to the value of message and go get the alphabet. So we're going to go to this string and we're going to look up a number, right? We're basically saying we need to go to this string and we're going to use this as an index because then it's going to match up with the right thing. So to get that index, I need to get it from the array, right? So I'm going to go to the array and say, please give me whatever number is at index I in that array. So maybe it's 18 or 9 or 7. That number is going to serve as my index for alphabet, and that's going to give me the correct letter, and then I will tack that onto my message. Okay. So then once we're done iterating through, we return the message. Okay. So now we've got our test data. We can go ahead and decode this. So I'm going to say, we need to print it because it's just coming back as a string, right? I will call using the alias read message in lights and pass in message 1. And let's see, let's see. And we get right here, that's the message right here. And then we can do it again with message 2. Uh-oh. Oh, just happened. Okay, I got rid of my screen. I have no idea how that happened. Okay, hit something. There we go. That's what I meant to do. All right. And no. Yeah, let's call this. Okay. Run it again. Okay. And now the second message says run, right? So now we have our messages from Will in the upside down. And we used this constant as the alias to call the function that we defined in that same line of code right there. And it ran it for each array that we provided for it. Okay. So why would you do this? What's the point, right? This is going to be a very popular way for you to code with the React library. You're going to create a lot of functions, and this will be this is the way most devs do it that code in React. And so we'll be looking at that in chapters 29 through 31. So you'll want to be, at least a little bit familiar with this by the time we get there. There's also another syntax, and we're going to talk about this in chapter 28, called an arrow function. You're also going to see this in the wild. You probably have already run into it. You've Googled something like, how do I do such and such? And then some Stack Overflow, question has come up, and you've seen a bunch of very haughty devs, with lots of one-upmanship and things like that. Yeah, people can be jerks on Stack Overflow. But anyway, and they've given their answers, and you probably have seen some arrow functions. And if you haven't yet, you will. We're going to teach you that. For now, you can just use the syntax I'm teaching you today, no problem. There are other uses. Anonymous functions are often used if you just need them one time. You don't really need that function to be reusable for other purposes. So just define it in place, right? And so, yeah, you don't need to give it a name or store it in a constant or anything like that. So, the most common use for this is with higher order functions because you actually have a function that takes a function as an argument. So that's what we're going to look at next. Let's see. But I want to just stop and see if anybody has any questions before I talk about higher order functions.
I'm seeing shaking heads, so I think we're good to go.
Okay. All right. So yeah, let's talk about higher order functions. We'll go back to this concept of a black box, right? If a function can be flexible and accept other functions, we can make it work for a lot of different uses. And that's what a higher order function is. That's one definition of a higher order function, is that a function that can accept other functions as arguments. So let's say we have a function calculate, and we give it two numbers, and then we tell it what we want to do with those numbers by passing in another function. And you can imagine, I'm not giving you the definitions of these functions, but you can imagine what they do, right? They just return numbers with whichever operation that is. So I say calculate 3, 2, and add nums. What do I expect to get?
5.
Yeah. And if I say calculate 11 and 9 and subtract nums, I'll get
2.
Yeah, and so on and so forth. If I'm going to have it multiply, I would get 30 with 5 and 6. If I'm going to have it divide with 12 and 4, I'd get 3, right? So a single function calculate can then be very flexible because we actually pass it along another function for it to run with whatever else, data we're providing for it. That's the idea of a higher order function. Make something that can actually do, work with a lot of different things. Okay. So if you were to define a higher order function, you have to remember that parameters are just variables, right? And we've just learned how to do that, creating aliases for other functions. So you would assign a parameter with a name that sounds like a function name, but it can be kind of generic. And then, of course, don't put parentheses. You're not trying to call anything. You're just creating a variable, an alias to represent that function. So that would be your parameter. And then inside the function body, you use that alias to call the function. And then it doesn't matter what function's been passed in, you have a way to call it because you're just using that alias. You can do this by passing in an existing function. This is one way to do it. So if you already have a function that exists that has a name, you can just pass that in by name by reference. So this is why it's important to understand the difference between calling and referencing. So here's an example. I've got a function called getFancyJoin, and its job is to take an array, join it together as a string, and use this connector space asterisk space, and then make it uppercase. That's my fancy join, okay? Let's say I also want to process I want to go through an array of items, and I want to process it and say, print this formatted. So I give it whatever items I want to give it, and then I also decide I want to be able to pass in a function so that I can format it however I want. It may be this function, it might be something else. I need a generic name that just represents any function I want to use for formatting. So I'm just going to call it format. That's my verb. I want you to format what, these items, but this will be the alias for whatever we decide to use. So then I can just say print, and call format and pass in items. And that's the job of this function, is just to print it formatted, okay? So I start with some real data to practice on, and I say, okay, let's take food and do apple, fish, and milk, which does not sound like a really great combination, but we'll go with it. And then we want to print formatted. So what would I pass in first?
Food.
Food, okay, and then what would I pass in second?
getFancyJoin, I think was an answer.
Yes. Yeah, I'm going to go ahead and use this named function up here, and that's going to be the specific way I want to format it. So I'm going to let this function use that function by way of having this alias. Okay, and then we get, in all caps, apple, fish, and milk separated by that, connector, the space asterisk space. Okay, And it prints out directly from, after I call this function and pass those in. Okay, that's the idea of using an existing function and just passing the name in by reference. We're not calling it, we just refer to the name. Okay. Again, that's a parameter. This is the argument there with the functions. Okay. What if you have one that's just a one-time use? You don't already have an existing function. You don't really need to store it. We can do that too. We can just, put it in place. We can just define it and just pass in the definition directly. So it's going to execute because you're still executing the higher order function, but it's not going to bother storing the definition. So we just used print formatted with our food and with get fancy join, right? Now I want to use print formatted, but I'm going to use a different array here. I want to actually format these tools. And instead of doing the fancy join, I have one way I want to do it, but this is really the only time I need it. So I'm just going to define it in place. So everything from, the function keyword here down to this curly brace here where you have the end of the function body, that entire thing is the definition. And then the parentheses after it is where you're just closing it because that's your second argument that you're passing in. And there's the beginning of those parentheses. The first argument is the array. The second argument is a function. But if you're not referring to an existing function, then just provide the definition right here, right? So we'll do that. And then we just say it'll take an array of some kind, and which of course is going to be this. And whatever array that is, the result is going to be the string building thing where we just go through and capitalize everything and then also put it on the next line. So we're going to see them one line after another. So when we do that, the result of calling print formatted, passing in tools, and then passing in this function definition is drill, hammer, and saw, all capitalized on separate lines. So because we created one string that had those line breaks in it, and so when it printed it, that's what we get. Okay. I'm going to do some examples for you in a second. But first I want to actually show you some built-in higher order functions in JavaScript. Your chapter mentions one of them, which is map. So I'm going to demonstrate that. But there's another one that I'm just going to give you some bonus knowledge that's very common, and that's for each. It's another way to loop. So let's do each of these in turn. The first one is map. This is, again, built in. It's actually a method of an array, which means you call it on your array. A method is just a function that's attached to an object. So we will take the array and call the method map, and it just creates a new array from an existing array. So here's how it works. You give it the function that you want it to execute, but that function is not to execute on the entire array. It's to execute on an element of the array. So what it'll do, map is what will iterate. And then every time it gets to a new element, it's going to execute the function you give it on that element. And then it'll push that result to a new array that it's kind of keeping in the background for you and building that array up. So it's basically an accumulator pattern. It's just doing it behind the scenes. And then it just returns that new array. That's the return value of map. So here's an example. We've got some flowers, rose, lily, and tulip. We actually want to, let's have a named function capitalized where we take a word and do this. Okay, we saw this already. All I have to do is log the return value of saying flowers.map and giving it capitalize, and it goes through every single one of these and operates on it, and then gives us a new array with the same elements transformed by this function, which just took a single word at a time. Okay, and that's what we end up with. Okay, so let's go over and do an example of this. Come down. Okay. We're going to write a function first. I'm going to use a named function. So we're going to create the function that we want to use for a single element first. And the idea here is that we need to convert a number into a string that has a length of exactly 3 with leading zeros for the tattoos for the children in the Indigo Project, okay? Because they all have these tattoos on their arms based on their number. But there's always leading zeros, and it's always exactly 3 long. So we're going to write this function first, and I'm just going to write a regular named function, get subject tattoo, and I will give it some sort of number. And then what I'm going to do is say, we need to find out the number of digits, first of all, right? How many digits does this number already have? So I'm going to convert convert number to a string first so that I can count its digits and get the length. Okay. Once I have the number of digits that already exist, I can figure out how many zeros I need. And so I'll just create those using repeat. So I'm just going to say, give me the number of zeros with repeat that is 3 minus however many numbers of digits we already have. I only need zeros to fill that out to get to 3. And then we can return zeros plus num concatenated together. However many zeros we have plus the original number, and then it should be 3 characters long exactly because of the way we did this. Okay, so that's going to operate on a single number. What we want to do now is produce a new array that has all of the tattoos formatted correctly for all of these. So we're going to use map to do that for us. So I'm going to store it in a variable and then we'll print it. I'm going to say let tattoos equal, and then we're just going to go to the data that we want and say, take this data and map over it and use this as the function that you're going to use to operate on every single one of the elements. And that's important. This does not operate on an array. It operates on a single element. Map will take that and apply it to every element. And I know I'm repeating myself, but I'm doing that on purpose because it takes a while for these concepts to sink in. Well, do I remember when I was learning it for the first time. Okay, so let's do it. Let's go see how this turns out when we say, take this array, map over it, and give me a new array that has new elements after they've been processed with this function. And there we go. We have a new array, and every single one is a string that has all of the numbers with leading zeros, and they're all exactly 3 digits long, which is what we needed. And you can imagine that this kind of application, it could be, I mean, we're using silly examples, but a real world application, you may need something done a certain way. And you need to transform your data into a new array of slightly different values or whatever. This kind of process can be easy and, easy to do with map, because all I did was tell it what data, call that built-in array function map, and then just give it the operation I want it to do for each element. That's it. And then I had myself a new array. Okay. What if you wanted to do for each? So here's the bonus knowledge, guys. This is also a built-in array method. So we'll call it attached to an array. And you just loop over something. It doesn't return a value. It just gives, you just give it the function to execute and it'll do whatever you want. I mean, really, you think about the way you do a for loop. You can set up the body of a for loop however you want, right? And tell it what to execute every single time. We're doing the same thing. It's just that in this case, we're just, using this shorthand of calling this thing, and we're just telling it what it is as a function. So here's an example of how I'm doing it anonymously. I'm saying I don't need to have a named function that like capitalize or whatever that we were using before. I'm going to just do something very specific. So I'm just going to define it in place and pass that function definition to for each. And then it'll run this function for every single thing in the array. But it doesn't produce anything. And especially, I mean, it's just printing for us, right? And it's going to just print each one. So you already know how to write a for loop to do this. This is how you do it with for each. You would just do this, and then, it'll process this for every single one. And of course, the result is I am eating a delicious apple. I am eating a delicious orange, etc. Okay. That's for each. Let's go do an example. And we'll practice using the anonymous function as the argument instead of using a named function this time. So we've got the Hellfire Club, and we're going to use for each to operate on that array. And we're going to just print out a sentence with each person's name. So all of them should say, name is a member of the Hellfire Club, unless it's Erica. If it's Erica, it should say Lady Applejack, the most badass member, instead of member of the Hellfire Club. So let's do it. I'm going to start by just saying Hellfire Club for each, dot for each. And now I provide now I can finish it like this with a semicolon, but between the parentheses, I need to provide my function definition. So that's going to look like this. I'm going to have, a function definition. My parameter is going to be name. And then I'm going to actually, give this kind of an easy to read proper formatting by splitting this out and putting it on separate lines. So I can say if name is Erica, then we need to print something very special. So console.log, and I'll do a template literal here and say name is Lady Applejack, the most badass member of the Hellfire Club. Okay. Otherwise, if it's not Erica, we're just going to print a basic sentence for that, right? So I'm just going to copy this down and member it, and we'll just say a member of the Hellfire Club. Okay, let's run it. All right, there we go. Eddie is a member of the Hellfire Club. Gareth is a member of the Hellfire Club. And we keep going until we get to Erica, and she is Lady Applejack, the most badass member of the Hellfire Club. All right, so that's the idea. It just goes through and iterates. It performs whatever you want it to on every single element, and you represent that element with this variable that's the parameter here, and then it just takes it and runs with it. So you don't have to have, with this type of syntax, you don't have to have something like I to represent an index and then access it with bracket notation. You skip past that and just use a variable name to access the element instead. You're not expected to use this anytime soon. You can keep using regular for loops, but this is another example of a higher order function, a function that takes a function as an argument. All right. Any questions about higher order functions?
Does not seem it.
Okay. Let's take our 5-minute break. When we come back, we have lots more to talk about. Welcome back. It's time to talk about recursion. We are going to break this down a little bit at a time, hopefully help you wrap your mind around it. So this idea of recursion means that you call the function from inside itself, which might sound a little crazy, but it's really useful in certain situations. It can be very efficient when you have a complex problem that can't be solved, in other ways, linearly, where you would just start from the beginning and go through from the beginning to the end, like, going through an array or through a string or whatever. So the approach is divide and conquer. Let's split things out, and we'll keep going and, calling the function from itself with slightly different, bits of data until we find a base condition. This base condition just means, what it is that we should tell it, to stop. How do we know when to stop recursing so that you don't end up with infinite recursion, which works just like an infinite loop? So when it takes this approach, you will sometimes see these return values, coming back in reverse, because it's calling, and then returning. So here's an example where we do a factorial. This is a classic recursion example. We say, 3 factorial. So that means 3 times 2 times 1, right? But if we do this with a formula, we basically say, we just need to take n and multiply it by n minus 1 factorial. And then that, we can ask again and say, hey, can you do that with the next number in line? So, if we have 2 times 1 factorial at this point. It's the same formula every single time. We just keep, changing what the number is. When we get to our base case where we get to 0 or 1 in this case, we say, okay, we're done. We have no more factorials we need to calculate. So let's start returning numbers. So this returns 1, this returns 2 times 1, this returns 3 times 2, and then our final value ends up being 6. So that's the idea here. And so I'm going to look at this in terms of the actual code. Like, it's like, okay, great, that's a diagram. I think I sort of might understand that, but how do I do it with code? Let's break it down. There's really 2 things that you need to do. One is to, just remember that it's about divide and conquer. So you have to have, one range of numbers or whatever it is at a time. In this case, with this factorial, that's exactly what we're doing. We're working with numbers. Or maybe you're working with an array of elements. You would like maybe remove an element for array and then operate on the rest of the array or something like that. There are lots of different ways that you can approach it depending on what it is you're trying to do. But ultimately, you have to return an expression that will call the function on one or both of these pieces of data as you're separating them out. And that's essential. And so you have kind of one structure that you could choose to use would be this idea of having an early return for the base case. Otherwise, you just keep recursing. That's kind of typically how I like to lay this out. It helps me remember I have to have a way to stop this thing, but unless we're there yet, we need to just keep calling it. So in this case, let's focus on the second part, where we're actually saying, what is it that we want to repeat over and over again, this recursion? If I'm doing a factorial, then I want to use that formula n times n minus 1 factorial. So I'll do that. I'll say return n times recursive factorial n minus 1. I'm calling my own function and just passing in the next number down and multiplying it times the current number. So then it calls the next number and it goes through. And if we're not all the way to the base case, it's going to keep going. That's one part. But the base case, this base condition is essential. So it would just continue infinitely if you don't tell it when to stop. So you have to think about what problem it is you're working at and how it is you would tell. If it's a number, maybe you're trying to get it down to 1 or 0. If it's an array, maybe you're just waiting until the array is empty and then you return some value at that point. So you'll have to, think about it depending on what you're trying to do. And that is what you check for conditionally. And if so, then you would do an early return. So this is how I like to lay it out. But remember, I think the thing that was always hardest for me when I was first learning this is remembering that meant I had to have 2 different returns. I don't just say n times recursive factorial and give it n minus 1. I have to return that value because if we're recursing, we have to keep returning back, returning every time we recurse. But for the early return, you're also going to use the return keyword. So in this case, we would say, okay, when we get to n equals 1, then we know we're done and we can just return n and not have to call this again. And then as it's like, multiplying it back and returning all those values, it will eventually get to our final case. So I have some examples where we're going to do exactly this problem, and we're going to examine what's happening behind the scenes as we do it. And so this is a linear way that you would solve a factorial, right? You would just say, okay, let's just, start with an initial result of 1. Go maybe start with n as the last number and go all the way down until we get to 2, greater than 1, because we don't need to worry about 1. And then we're just going to decrement each time and reduce it. And then we would just say, multiply the result times I. And so we have 3 times 2 times, times 1, right? And then just return the result. That's linear. We can certainly call this. I'm going to uncomment this and we can run it. Okay. And we see this incredibly big number because I passed in, what did I pass in, 15? Yeah, 15 factorial is like, a very, very large number by the time you multiply all those numbers together. Let's write our recursive function. So again, I'll give it a name, recursive factorial. And we're just going to pass in a number. This is the number we need the factorial of. So I need a base case to stop the recursion, and then I need, otherwise we recurse, right? So the base case is if n is 1, then we're done, and we can just return n or return 1. Actually, in that case, it doesn't matter. In this case, we need to actually just return n times recursive factorial and then go to the next lowest number, n minus 1. All right, so let's test it. I need to actually print it, don't I? Yep. It's returning the value, so I need to print the value so we can see it. All right, and we'll give it 15 so that we can see if it's the same number. And prove that it works the same way the linear one does. Okay. Yeah, and it does. Something that can be interesting is to you're familiar so far with console.log, right? There's this thing called console.time and console.timeend that allows you to start and stop a clock so you can see how fast something is. Sometimes recursion is much faster than solving something linearly, and sometimes it's not. So this would be an interesting little way to test this. We could actually, right here before we do the linear factorial, we can start the clock by saying console.time and pass in a name. And I'm just going to call it linear factorial so that we know what we're looking at. And then after that, I'm going to do console.timeend. So I'm going to do like that and give it the same name. So it knows this is the one I'm starting, and then I want to stop that same one. So then I can do it again here, and we'll check console.time for the recursive factorial. And do time end. And let's just check it out. Let's just see how efficient these are. Okay, so the linear factorial completed in 0.248 milliseconds. The recursive factorial completed in 0.033 milliseconds. It was actually quite a bit faster. So that's an interesting little experiment, right? I'm going to take that off for now. And what I would like to do is put in some console logs so you can see what's happening behind the scenes as it executes on all of this. So let's start with just saying, which one of these are we on, since we're calling it multiple times. So I'll say function called for, and we'll just check and see what the value of n is when the function's called. Whether it's the very first time or if it's when we're calling it here as part of the recursion. That'll help us see that. And then in the base case, we could say, something like all done. I have to actually put that in quotes though. All done. And then here we could say, let's check and see what this next value is going to be. So I can't return it yet. If I want to console log it, I need to give it a name. So I'll say next value equals, and we'll store it and then return the stored value. And then in between there, we can actually log it and say next value. Okay, but let's even just say, if we get to this point and we haven't had our early return, let's also log the fact that we are doing that. I'm just going to say calling function again for, and I'll say n minus 1. And that way we can see, we're going to see that, and we'll also see it when it gets called again, but you'll see the difference. It's happening when we reach this point in the code, and then we call it, and then that means it's going to start at the top here for the new number. Okay, let's run this, and then we should see all these console logs, and it'll kind of tell us what's happening behind the scenes. Okay, so notice that we have all of our console logs first. Function called for 15, calling function again for 14. Function called for 14, calling function again for 13. It goes all the way down until we get to 1. And then it starts, it says all done, which was our base case. And now it's returning those values back, 2, 6, 24, until we get all the way to the very last number. And then of course we also logged it after that. So it logs it again. But this is what's happening behind the scenes. It's processing through all of them first, and then it returns all the values second, just like I had in that diagram. So that's kind of interesting, because it can be hard for you to imagine, how is it processing all of this in order? And that's a good way to do it, is just to check it with these console logs. Okay, I'm going to comment those out so that we don't continue to see all that until later. Okay, so I want to do one more example, because I showed you how to do factorial. There are other applications, right? One such application would be, what if you have an array like this, that is an array of arrays, it's multidimensional, but you have no idea what the structure is and how many levels deep it goes. You can't just set up a bunch of nested loops for that, right? Because you don't know how many times you need to nest and loop. So recursion is great for that because you can divide and conquer. So here we have the Hawkins lab. It has a whole bunch of floors. It has different numbers of rooms on each floor. So like this one has 3, this one has, 2 different areas. This one has 3 different areas. And then some of those areas have, are broken down further into smaller rooms. But we have no clear pattern for this. So let's use recursion to actually count up. And these numbers represent the number of demo dogs that are roaming free inside the Hawkins lab. RIP Bob, right? So we're going to plan this out first. We need to ask ourselves some questions. What is the base case? Is there only one base case? And if we look at this, we're basically saying, okay, if we're going to divide and conquer, we need to talk about that strategy too, right? And we basically just need to say, as long as we don't have an empty array or just a number when we come across a number, then we're going to need to recurse, right? That's really, and so we're just going to keep dividing it up. And maybe we could split the array with something like pop or shift that, takes a value out and keeps making the arrays smaller until they're empty. We could do that. And then that would mean our base case, we have 2 base cases. We have, what happens when we get to just a number? What happens when we remove these and we just have an empty array? Then we don't need to continue to do anything with this element anymore. And then of course that holds true for this entire element here that's part of the greater array. So this is how we're going to just, divide and conquer and break it down. Let's, okay, so again, number 1 was if number, add to count and return. We're going to be counting these up as we go. And then the other case is if it's an empty array that we have discovered, return 0, because we don't need to add anything to it if it's just empty, right? And for dividing and conquering, we're just, I'm going to say, let's just go ahead and use shift. We'll take off the very first number we come across instead of taking it off the end. It'll be easier, I think, for us to conceptualize how this is happening if we use shift. So I'm going to use shift to remove and add, and then and add whatever is returned from recursion with the remaining data. Because if we shift it, that data is no longer in there, and we have a mutated array that we can pass on and recurse on. Okay, so we need to define the function. Now that we have a strategy, I'll say count demo dogs. This is our function, and we're just going to pass in our data, whatever that is. In this case, it's going to be the Hawkins lab. And so we'll do our base case, and then we'll do our recursion. So base case is if the type of data, because it could be another array that's an element, or it could be a number. So let's just say if the type of data is a number, then all we need to do is return the data. And then we can have another condition possible, another possible early return that says if data.length is 0. So if it's not a number, then we can assume at that point that it's still an array that we're working with, a nested array. Then we can say return 0, because we're not going to add anything new. Otherwise, we're going to recurse, and so we need to return a recursion over data.shift. Now this is going to be a little confusing at first. I'll explain it. And then we're going to recurse with the rest of whatever's left over after we shift that value off. Here's the thing you got to remember about array methods like pop and shift. When you evaluate it like this and you say, array.shift, it returns just the value that you're shifting off. That's what we want to count. We want to make sure that's added in. So we're going to count whatever's been shifted off the array. Then we're going to add everything that's, we're going to recurse and start at the top and add whatever data is left and run that again. And that's how we're going to keep adding on all the values that are returned. So next time it goes around, it might return here, or it might continue to return here, but it's going to continue adding those numbers up, because here we're removing the data, and that's what this represents. Here's what's left over after that's been shifted off. We can refer to it immediately in the same line, and that number has already been removed. And so this is what's left over. So I'm kind of doing things in a single line here. If you wanted to break it down, you could say let, in fact, let me just do it just so you can see, just so this is maybe I'll break it down. So let number to remove be, actually, I shouldn't say to remove, I should say removed, because we're doing it while I do this. We're removing it. Data.shift. That's the number. But the data has now been shifted, which means I can just, pass on data as it is now, because this has already been done, and it will no longer include that element. Okay. So that's how we're going to do this. We're just going to keep breaking it down. So the very first time we call it, it's going to shift this entire thing. And so we're going to say, okay, let's call our function again for this, and then we'll call our function for what's remaining in the original array. And we'll just keep going like that. All right, I can call it, and we're going to get a result. But then you're going to be like, wait, so what happened again, right? Oh, I see. Okay, Hawkins lab. Yeah, I see what I did. Okay, that's all right. It's a little bit different than my solution, but it's all right. So we're going to run this, and we see 66. There are a total of 66 demo dogs in the Hawkins lab by going through this. So you're like, well, that's great. It worked, but how did it work? So now let's do, just like we did before, we're going to put some strategic console logs in here so we can see what's going on. I'm going to do a console log here just to see the data. Let's just start with that. Every time we call this, what is the data at that point that we're actually, seeing as it goes through? Let's run it that way. Okay, so we see a lot of things happening here. First, we have the whole data, the very first time we call it, the entire array with all of its subarrays. Then it pops off this, and we go to run that. So we have, this is data. And then it continues recursing just within there. We haven't even seen the rest of the data yet, right? This is how recursion works. It just keeps drilling down and drilling down. So it's going to take this and pop off the 6-2, and then from there, it'll pop off the 6 and then handle the 2, and then we have an empty array. So it's not linear by any means. It's digging down and drills all the way down until it can't drill anymore. And then we're going to see the result of the remaining things that we already called. Okay, also recurse over the rest of this array. And then we see that being broken down further, and so on and so forth until we either have numbers or we have empty arrays, and that's what stops it. And that's where we see it pick back up with whatever was next with things that aren't down to their base case yet. So that's how we see just everything from the top. If we go a little bit further and just log some things so we can see, very specifically what's happening here, we could say like, adding the number data to the count. When we actually return whatever that number is when we finally arrive at it. And then here we could have a little console log to say, oh yeah, we found an empty array, right? Empty array found. And so we're just returning 0 and adding that to the count. Otherwise, down here, we can say recursing. Oh, I have to log that, don't I? Getting ahead of myself. Okay. All right, let's run it again. Okay, this is long. We got a lot going on. Okay, so we called it and it skipped over the base conditions. There were no empty arrays or numbers found. We actually have a pretty complex nested array still. So it just says recursing, and then it starts breaking it down, recursing. It finally gets to a number, adding the number 6 to the count. Here, it has what's remaining from that, and it has the 2, so we're recursing. But then it finds it and adds it to the count. Then it finds an empty array, so it just adds 0. And now it picks back up with the next thing that it was broken out from, separated here from this. And once it's done with all of that, that's when we see it pick back up with the remaining stuff from here, these last 2 elements. And then it just goes from there. So adding these kinds of comments in can help you understand what's happening behind the scenes because it happens in a split second. But if you want to understand how it's moving through and divvying up all these pieces, this divide and conquer strategy, this can be a good way to start to understand what the sequence is of events before we finally get to our number when it returns everything that's been added. Okay. Do we have any questions?
Tucker. Okay. So I think to sum it up, it's the difference between using return and break. Yeah, the difference between using return and break in a recursive function.
Yeah. Okay. Break only works with loops. And we're not looping. See that?
Yeah, we got a thumbs up.
Yeah. Break is when you're breaking out of a loop, and we're doing something that iterates, but it iterates differently because of the way this works with recursion, where we're calling the function over and over again. And that's, I think, that was one of the hardest things for me early on to understand, is that all of these returns are necessary because ultimately it all has to add back up. And so depending on which return it's coming from, you're either going to keep going or you're just going to return some value from your base case. But you're adding up the results of, calling this when you divided, one number out from the rest of the data. And so, yeah, there's no breaking. You just have to return until everything comes back together. As it all got split out, now all those values are being returned back up to the top to make one number. Yeah. Any other questions?
Okay, so the question is, why does it stop when it stops? How come it doesn't just keep adding 0? So I assume you're talking about line 178 or line 184. Yes, it kicks it back up to the top again. So how come that? Yeah, the last time 184 runs, what is happening?
Okay. Yeah, let's look at so when it finally got done here, removing 11 and adding that to the count, all that was left were empty arrays. And so that's why we had it just return 0. And at that point, it's no longer even, the code isn't even getting down here anymore. That's the importance of the base case and returning something here, is that you're stopping it from continuing down to here. You're saying, oh, I'm done. So I can just return this, and every time you call it, you're going to get a return value, and they're going to get added up here the way we've done this. But ultimately, you're not actually getting down to here. So it stops those branches and it just, moves on. Does that help? It's like, if you can see my hands,
Yeah.
it's like, you have, a tree essentially, like with all these roots coming down, right? And every once in a while, it's going to get to a point where it just doesn't continue because it reaches a base case. But ultimately, everything, no matter where it stops, it all goes back to the original point that it started from. And so you'd only branch off and create more of those branches whenever you actually get to this code down here. But as long as you've stopped it from here, then it's done, and it's just gonna return that. So, maybe this represents a 0. Maybe it represents a number. But if it does, it means that it's, when it calls it this time, no matter which recursion you're on, when it calls it this time, that's just going to add in a number. And if it calls it this time and both of those are base cases, then it's done.
We're nodding.
Okay. Yeah, this is mind-blowing stuff. It's very hard to get your head around at first. It's okay.
This is brain pretzels. Anyone else have any questions? No, I'm seeing shaking heads.
Okay. All right. So I have things to help you practice a bunch of things about functions. And I feel like at some point I did something with recursion, but I can't remember. But you can look and see if you want more practice. So we have another GA work. Tomorrow's the big day, right? Get that graded assignment done and in. Work with your IAs on that. If you are ready for it, we will have that self-assessment exam, and I'll go over in the morning how that's going to work, those exams. Then Monday, when you all come back after, resting your brains for the weekend, we'll talk about objects. And then we'll talk about modules on Tuesday. And I will also introduce graded assignment number 2, because objects is the last thing you need to get started on graded assignment 2. And then you'll have a work day on that the next day. And I'll do another review session that day. Okay. For Studio today, you're going to write some functions to sort numbers. You're going to investigate different ways to go about sorting numbers, because you may remember that the sort function, the array method sorts alphabetically. So it just looks at the very first digit of the number, even if it's a number. If you want to actually sort numbers properly from negative to positive, you have to have a different way to do it. So this will help you kind of investigate all of that and come up with some different solutions. And bonus is to do a recursive solution, so you can play around with that.